All right, get ready to dive in. Acids, bases, and salts. That's what we're tackling today.
It's amazing how these things are everywhere, really.
Yeah, like literally everywhere.
I mean, think about it. That lemon juice you put on your food? Acidic.
Huh. And soap.
A base.
So we encounter these things every day, but...
But we need to be careful.
Oh, yeah, for sure. Not going around tasting everything to see if it's an acid or base.
Exactly. Some of those, some acids and bases can be pretty dangerous.
How so?
Well, they can be corrosive.
Corrosive?
Yeah, like they can cause burns and damage.
Well, right, like chemical burns. Ouch.
Exactly.
Okay, so we need a safer way to figure this out.
We do.
Some kind of test.
Yeah, a more reliable way.
And that's where indicators come in, right?
You got it.
Those things that change color depending on if it's an acid or a base.
Like a signal, yeah.
That's super
It's
rude.
like a chemical chameleon, you know?
I like that.
Changing its colors to tell us what's going on.
Okay, so what kind of indicators are we talking about here?
Well, one of the most common ones is litmus.
Litmus, okay.
Yeah, you've probably heard of litmus paper.
I think so.
It comes from lichens, actually.
Lichens, what are those?
Those kind of like plant things that grow on rocks and trees.
Oh, right.
So yeah, litmus is naturally this purplish color.
Purplish, yeah.
But if you put it in an acidic solution, it turns red.
Oh, so like a signal, red means acid.
Exactly. And if it's a basic solution, it turns blue.
Blue for base.
Yeah.
Got it. Okay, but litmus paper.
Hmm.
Don't really see that every day, do you?
You don't. But you know what you do see every day?
What? Turmeric.
Turmeric. The spice.
Yep, that same one.
What does it have to do with acids and bases?
Well, turmeric is actually a natural indicator, too.
No way.
Yeah, it's pretty cool.
I mean, I know turmeric stains like crazy.
That's right. And you know how those stains turn red when you wash them with soap?
Wait, is that because of the soap?
It is. Soap is basic, and in a basic solution, turmeric turns red. Wow. So it's like a little chemistry experiment happening right in my laundry.
Exactly.
That's pretty awesome. So we've got litmus, turmeric.
Mm-hmm.
Any other natural indicators we should know about?
Oh, definitely. China rose petals?
China rose petals.
Yeah. You can actually make an indicator solution with them at home.
Cool. How?
Just soak the petals in some warm water, and it turns this magenta color in acidic solutions and green in basic solutions.
Oh, magenta and green.
Yeah, pretty vibrant, right?
Okay, so these indicators help us identify if something's an acid or a base.
Right.
But what happens when an acid and a base, like meat?
Ah, that's when things get interesting.
What happens?
That's called neutralization.
Neutralization.
It's when an acid and a base basically cancel each other out.
Oh, like a chemical showdown.
Exactly.
So how does that work?
Well, to really understand it, let's bring in another indicator.
Another one?
This one's called phenolphthalein.
Phenolphthalein. That's a mouthful.
I know, right? But it's
Right.
perfect for neutralization reactions.
Okay, so what does it do?
Well, it's colorless in acidic solutions,
Colorless, okay.
but it turns this bright pink in basic solutions.
Ooh, pink. So how do we use it to see neutralization?
Okay, imagine we have a clear acidic solution, right?
Okay, I'm picturing it.
Now we add a drop of phenolphthalein. Nothing happens. It stays clear.
Right, because it's acidic.
Exactly. But then we slowly start adding a base, say sodium hydroxide.
Okay, adding the base.
At first, nothing happens, but at a certain point, boom, it turns pink.
Whoa, so the pink means it's become basic.
You got it. And if we keep adding base, the pink gets even stronger.
Wow, that's pretty cool. And what if we add acid back in?
Well, if we carefully add a drop of acid back to that pink solution,
Yeah.
it goes back to colorless.
No way. So it's like a reversible reaction.
Exactly. The acid neutralizes the base, bringing the solution back to neutral.
That's like a magic trick.
It is pretty amazing.
But wait, you mentioned something about heat earlier.
I did. Because neutralization isn't just about color changes.
What else happens?
It's a chemical reaction that releases heat.
So it gets hot.
It does, like a mini explosion, but without the boom.
Whoa, okay. Anything else?
One more important thing. Salt.
Salt, like table salt.
Yeah, but not always that specific kind. Salt is a product of the reaction between an acid and a base.
Huh, I never knew that.
It's one of the fundamental concepts of chemistry.
So let me get this straight. Acid plus base.
Equals salt, water, and some heat.
Okay, I think I'm starting to get it.
That's great. And believe it or not, this seemingly simple reaction, this neutralization, it's happening all around us all the time.
Really? Tell me more.
Well, let's start with something we can all relate to, indigestion. Have you ever had to take an antacid?
Oh, yeah, definitely. What does that have to do with neutralization?
Well, that burning feeling you get, that's caused by excess stomach acid, right?
Right.
And antacids, like milk of magnesia, contain bases.
So you're saying
The base in the antacid neutralizes the excess acid in your stomach.
that makes sense. It's like a mini neutralization battle happening right inside you.
Exactly.
So we use it to fight indigestion.
Huh.
What else?
About ant bites.
Ant bites. What do those have to do with acids and bases?
When an ant bites, it actually injects formic acid into your skin.
Ouch.
That's what causes that stinging sensation. But you know what people use to soothe ant bites?
Well,
Baking soda or calamine lotion.
wait, are you saying those are...
Bases? They neutralize the formic acid from the ant bite.
That's amazing. I never knew there was so much chemistry going on with a simple ant bite.
There is, and it doesn't stop there. What about soil?
Soil.
You know how the pH of soil is important for plants?
Vaguely, I remember something about that.
Well, if the soil is too acidic, plants can't grow properly. So what do farmers do?
I don't know, add fertilizer?
Well, sometimes. But they might also add lime.
Lime. Like the fruit.
Not the fruit, no. This lime is a type of rock powder that contains calcium oxide or calcium hydroxide. And guess what?
It's a base.
You got it. Adding lime to the soil neutralizes the acidity, making it better for plant growth.
Wow, so neutralization is helping our plants grow too. This is incredible.
It is. And think about this. What about industrial waste?
Oh yeah, that could be a problem, right?
It can be very harmful to the environment, and a lot of industrial waste is acidic.
So what can we do about it?
Well, we can use neutralization. Factories can treat the acidic waste with bases before releasing it.
So neutralization helps protect the environment too.
Exactly. It's a powerful tool with so many applications.
Okay, hold on. My brain is trying to catch up with all this. Before we go any further, can we just recap the basics just to make sure I've got everything straight?
Absolutely. What do you want to recap?
Well, first, can you give us a final official definition of what an acid is?
Okay, so an acid is a substance that tastes sour, turns blue litmus paper red, and releases hydrogen ions, that's H plus A, when dissolved in water.
Okay, got it. Now what about bases? What's the official definition?
A base tastes bitter, feels slippery, turns red litmus paper blue, and releases hydroxide ions, OH, when dissolved in water.
Okay, so acids release hydrogen ions and bases release hydroxide ions, like a chemical tug of war.
I like that analogy.
Now for the last one, what exactly is neutralization, officially?
Neutralization is the reaction between an acid and a base, which forms salt and water and releases heat. Basically, it's the process of neutralizing the acidic and basic properties, leading to a more neutral solution.
Okay, that makes sense. And it's so cool to think about all the ways we use it in everyday life.
It is, and there's even more to explore.
Well, I'm ready for more. What other fascinating insights about acids, bases, and salts are waiting for us?
Let's talk about how acids and bases react with metals.
Oh, I remember doing experiments with those in school. I'm ready to dive back in.
Great, let's get started. So this pH scale, it's a really neat way to measure how acidic or basic a solution is.
Okay, yeah, I've heard of pH, but...
It's a scale, right? Goes from 0 to 14.
And what's in the middle?
7. That's neutral.
It's like perfectly balanced.
Exactly. Pure water, for example, has a pH of 7.
Okay, so what about the numbers below 7?
Those are the acids. And the lower the number, the stronger the acid.
So something with a pH of 1 is...
Super acidic.
Whoa, okay. Any examples?
Well, lemon juice, it's around 2.
2. That's pretty acidic.
It is, but you know what's even stronger?
What?
Stomach acid.
Oh, yeah, that makes sense.
It's got a pH of around 1.5.
Wow, that's intense. So low numbers mean strong acids.
Got it.
What about the numbers above 7?
Those are the bases. And just like with acids, the higher the number, the stronger the base.
Okay, so it's like a mirror image.
Kind of, yeah.
Any examples of bases on the pH scale?
Baking soda is a good one. It's around 8.5.
5.5, okay. Is that strong?
Not super strong. Now, something like household bleach, that's a lot stronger.
Bleach, huh?
Yeah, it's got a pH of about 12.5.
12.5, that's way up there.
Yep, that's why you got to be careful with bleach.
So we got this spectrum from 0 to 14.
With 7 right in the middle, neutral.
Acids on one side, bases on the other. But how do you actually figure out the pH of something?
There are a few ways.
Like what?
You can use a pH meter.
A meter.
Yeah, it gives you a precise reading, like a number.
Okay, so that's super accurate. Is there a simpler way?
Yeah, you can also use pH paper.
Oh, like litmus paper.
Similar idea.
Yeah.
But pH paper, it changes different colors depending on the pH.
Oh, I see. So it's like those indicators we talked about earlier.
Exactly. But instead of just telling you acid or base,
It gives you a more specific reading on the pH scale.
you got it.
This pH scale is pretty amazing. It's like having a secret code for understanding the chemical world.
It is pretty cool.
But I guess I'm wondering, why is it so important to know the pH of something?
Ah, great question. Because pH affects a lot of things.
Really? How so?
Well, think about your body. The pH of your blood, it has to stay within a very specific range,
What range is that?
around 7.35 to 7.45.
That's pretty narrow. What happens if it goes outside that range?
Well, that can cause some serious health problems.
So our bodies are constantly working to keep the pH balanced.
Exactly. And it's not just our bodies. The pH of soil affects how well plants can grow. The pH of water affects aquatic life, fish and stuff. Even the pH of certain foods, it can affect how they taste and how long they last.
Wow, I never realized pH was so important. It's like this hidden factor that's influencing everything.
It is. It's one of the fundamental principles of chemistry and biology.
Okay, hold on. I just want to make sure I've got this straight. So an acid is something that increases the concentration of hydrogen ions, those H plus things, in a solution. And that makes the pH go down. Right.
Perfect. You got it.
And a base does the opposite. It increases the concentration of hydroxide ions, the OH ones, which makes the pH go up.
Exactly. Acids and bases, they're always battling it out to control the pH.
Like a chemical tug of war.
That's a great way to put it.
Okay, I think I'm finally starting to understand this whole pH thing. But now I'm curious about salts. We know they're formed during neutralization, but what exactly are they?
Ah, salts. They're fascinating.
Tell me more.
Well, they're typically ionic compounds, which means they're made up of positively charged ions and negatively charged ions. Remember those from high school chemistry?
Ions. Vaguely.
So an ion, it's basically an atom or a molecule that's either gained or lost some electrons, giving it a charge.
Okay. And ications are the positive ones.
Because they lost electrons, right?
And anions are negative because they gained electrons.
Exactly, you're a natural. And in a salt, these oppositely charged ions, they attract each other, forming a crystal lattice structure.
Crystal lattice. Sounds fancy. So are all salts the same?
Not at all. There are tons of different salts, each with its own unique properties and uses.
Oh, like what?
Well, the most common one is table salt, which is sodium chloride, essential for cooking and flavoring our food.
Yeah, definitely can't live without that. Any other examples?
How about Epsom salt? That's magnesium sulfate. People use it to soothe sore muscles.
Oh, yeah, I've heard of that. So different salts, different uses. Pretty cool.
It is. And remember, baking soda, that's a salt too, sodium bicarbonate.
Wow. Baking soda is a salt. I use that for everything.
Yeah.
Cleaning, baking, even brushing my teeth sometimes.
It's a very versatile salt. But here's a question for you. Are all salts neutral?
Neutral. That's a good question. I guess I always assumed they were, since they're formed from neutralization. But is that always true?
It's a common misconception. While many salts are neutral, some can actually be acidic or basic.
Wait, really? How is that possible?
It all depends on the strength of the acid and base that reacted to form the salt. Remember that tug of war we talked about?
Oh, yeah. So if one side is stronger, it can kind of tip the balance.
Exactly. Let's say you have a salt that's formed from a strong base and a weak acid. The strong base kind of overpowers the weak acid, so the resulting salt solution ends up being slightly basic.
Ah, that makes sense. So it's not just about neutralization, but also about the relative strength of the acid and base involved.
You got it. It's all about that delicate chemical balance.
Okay, my brain is officially full of amazing chemistry knowledge.
Oh.
What's next on our deep dive?
Well, now that we've got a good understanding of acids, bases, and salts, let's explore some of the ways they react with other substances.
Like what? Give me a hint.
How about metals?
Metals. Oh, yeah, I remember doing some crazy experiments with those back in school. Let's hear it. Metals.
Ah.
Oh, yeah, I remember doing some crazy experiments with those back in school. Let's hear it.
All right, so picture this. You've got an acid and you add a metal.
Okay, I'm picturing it.
And what happens?
I feel like something should explode, but I know that's probably wrong.
Well, it's not exactly an explosion, but it's definitely a reaction.
What kind of reaction?
You usually get hydrogen gas.
Hydrogen gas.
Yeah.
And a salt.
Oh, so that's where the salt comes from.
Sometimes, yeah.
So this hydrogen gas, is that what makes the metal fizz?
You got it. You see those bubbles? That's the hydrogen gas being released.
Cool. But wait, don't different metals react differently with acids?
You're sharp. You're right, they do.
Like what?
Well, some metals are super reactive with acids.
Like even dilute acids can cause a big reaction.
Oh, wow. Okay. Any examples?
Sodium and potassium, those are really reactive.
Sodium and potassium, huh?
And these reactions, they get pretty hot.
Hot, like dangerous hot.
They can be, so you definitely don't want to try this at home without proper safety precautions.
Makes sense. So we've got those super reactive metals. What about the other ones?
The other ones, well, they react more moderately, you could say.
Moderately? Like what?
Zinc and magnesium are good examples.
Zinc and magnesium. Okay.
They'll still react with acids and produce hydrogen gas.
But not as crazy as sodium or potassium.
Exactly. They're a bit more tame.
So it's like a spectrum of reactivity.
You could think of it that way, yeah.
Okay, that's for acids. What about bases? Do they react with metals too?
Ah, good question. Bases, they're a bit different.
How so?
They don't usually react with most metals.
Really? So they're just chill?
Pretty much. There are a few exceptions.
Exception.
But for the most part, bases and metals don't really interact much.
Huh, that's interesting. So it's like acids are the reactive ones.
Yeah, you could say that.
Okay, that's pretty cool. Now I'm curious, what about all those applications you were talking about? You know, for acids and bases.
Oh, there are so many. We could talk about them for hours.
I mean, we don't have hours, but...
Right. Well, how about titration?
Titration, what's that?
It's this really cool technique used to determine the concentration of a solution.
Concentration.
And like how much of a certain substance is dissolved in a specific amount of liquid.
Oh, okay. But how does titration help with that?
Okay, imagine you have a solution of an acid,
Okay, acid solution.
and you want to know exactly how much acid is in it.
Like the precise amount.
Yep. Titration helps us figure that out.
Okay, I'm listening. How do we do it?
Well, you start with a known volume of your acid solution.
Okay, known volume.
Then you slowly add a base solution.
That base.
But here's the key. We know the exact concentration of this base solution.
Oh, okay.
Yeah.
So we're adding a base with a known concentration to the acid.
Exactly. And we keep adding the base drop by drop until the acid is completely neutralized.
Ah, I see. So it's like a controlled neutralization reaction.
You got it. And we can use an indicator to tell us when the neutralization is complete.
So it's like those color changes we were talking about earlier.
Yep. The indicator changes color at the end point, which means
Endpoint.
that's the point when the acid and base have completely reacted.
Okay, so the indicator tells us when we've reached the endpoint.
Right, and because we know the volume and concentration of the base we added.
We can calculate the concentration of the original acid solution.
Exactly. It's like a chemical puzzle.
That's pretty amazing.
Yeah.
Yeah, it's like we're using the reaction itself to figure out the unknown concentration.
That's exactly what titration is all about.
Okay, so we use a base to figure out the concentration of an acid. Are there specific types of acids and bases used in titration?
Well, we often use strong acids and strong bases
Oh, is that
because they react completely, which gives us a sharp endpoint.
sharp endpoint?
Yeah, the color change of the indicator is super obvious and sudden.
Oh, I see. So it's easy to tell exactly when the reaction is done.
Makes things a lot easier.
So titration is used to find the concentration of solutions. Where else is it used? Like what kind of real-world applications are there?
Tons. It's used in environmental science to test the acidity of soil and water.
Huh, makes sense.
It's also used in the pharmaceutical industry to make sure medicines have the right concentration of ingredients.
So it's about quality control.
Exactly. And in food science, it's used to check the acidity of things like vinegar and fruit juice.
Wow, so titration is really important in a lot of different fields.
It is. It's a fundamental technique used in chemistry labs all over the world.
This has been an amazing deep dive. I've learned so much about acids, bases, and salts.
Me too. And we've only just scratched the surface.
I know. It's crazy to think how much chemistry is happening all around us all the time.
Right. And the more we understand about it,
The more we can appreciate the world around us.
exactly. And make informed choices about the products we use, how we take care of our health, and how we protect the environment.
Well said. So to all our listeners out there,
Keep exploring
keep asking questions.
and keep that curiosity for chemistry alive.
Until next time, happy experimenting.
And remember, stay curious.